today's lesson, everybody, I'm going to use an analogy to try to help us understand. That's just one of my ways of teaching, and I feel like with chemistry, if you don't need it, don't use it, but if it helps, hopefully it does. So for our analogy to help us understand these trends, so that's what we're talking about today, are periodic trends. A trend is a pattern. Patterns that are all on the periodic table. Okay? Now, you will never have to know values. It's always about comparisons here. Because knowing a value is just a memorization. But based on these trends, you can predict a lot about something based off its positioning on the table. Okay? So for our analogy today, we're going to pretend that we as a class are an atom. Okay? I am going to be the nucleus of our atom. So I have what charge?
Yeah, you have a positive.
Okay, so I have all the positive. Okay? This is the one day where you're allowed to be negative because you guys are the electrons. Okay, now visualize with me here, people. It's not perfect, we have to move around, so just pretend, okay? So I'm the nucleus, imagine, because you gotta think 3D space, right? We're like a sphere, okay? The first row of tables, imagine as my first energy level. Now, where it's kind of false is technically only 2 are allowed on the first energy level. So, who gets kicked out? Just kidding. Okay? And then this would be my second energy level, my third, and my fourth. Okay? Okay, so to see if we're understanding, everybody point to who are my valence electrons in our analogy.
Wait, say that again?
Point to yourself. So you guys are the valence electrons. Okay, everyone understand how this works? Okay, now, before we talk about the trends, we need to understand things about forces, and that's what the Coulombic attraction activity was introducing you to, and it's the theme of all of the trends. Everything goes back to the fact that positive things and negative things feel a force of attraction. That's what Coulomb's law is. Coulomb's law, this is the fancy definition, but in simple terms, it's just that positive and negatives are attracted. Now, it's attracted by 2 factors. So if you want to know if it's going to increase in force, one of these 2 things has to change. So the 2 things that affect Coulombic attraction are charge and distance. So in terms of our atoms, what we want to look for are 1, if there's more protons. The more protons I have, the greater the force to the electrons there is. Second thing that also affects it, though, is distance. The farther away something is, the less attraction it has. Okay? So 2 big things today to pay attention to are charge and distance. If something is changing, one of those 2 things have changed. Okay? All right, with our Coulombic attraction and this force, we also have to take into account another force. How do you guys feel about each other, though, if you're both electrons?
Unless we're going opposite ways.
Now start spinning. Okay, so there's lots of forces, people, that go on. Make sure I cut this out of the video. Okay? So there's a force between the nucleus and every single electron. But the electrons to each other are repelling. So what we get is what is known as a shielding effect. So not only are my valence electrons, so Hannah, wave your arm for me. So not only is she really far away, so that decreases the force, but all you people in between also shield the force from reaching her fully. That make sense?
No, I was just repelling my friend.
So when we use the word shielding, okay? Shielding refers to inner electrons. So first 3 rows, you guys are the inner core electrons. You are shielding the valence electrons from feeling the full force of the nucleus. Now, technically, the only group that feels the full force is the first row.
Yes.
You guys shield the second row. But that's why the shielding gets even more. The more electrons you have, the less of the force can get through. Okay, so when we use this word shielding, that's what we're referring to. Now recognize that people on the same row, so Ethan does not shield Kasich because they're the same distance away. And the interesting thing about the force is it's not divided because there's more, it's just about the distance. So as long as you're the same distance away, it's not like the force gets cut in half because there's 2 electrons to share it with. Yeah?
It's kind of like gravity. So if you have one tennis ball and you drop it, it's going to hit the ground with the same amount of force. If you have 2 tennis balls, they're not going to hit the ground with half the amount of force. They're going to hit it with the same as well.
Yeah, great example, right? It's not like divided, because it's kind of like that weird thing of like when you ask your mom, like, who do you love me? And she's like, I love you all equally. Like, and it's kind of like that, right? Okay, now, this term of force has a name. It's known as the effective nuclear charge. Its abbreviation is a Z with the subscript EFF. So I call it ZEF. Okay, so as we talk about ZEF today, everybody, ZEF refers to the force of attraction that an electron feels to the nucleus. Now, it's always less than the full because of the shielding effect. Only row 1 feels the full love of the nucleus. Okay, the rest of you, it gets stolen a little bit because you're farther away. You know, if you're on the front row, it's like a sign, right? I guess. Okay, so we're all going to know what I mean when I use the word ZEF today, right? Okay. Okay, here we go. First trend of the day. Atomic radius. So first we're going to define the trends, and then we're going to classify them based on how they change on the table. So we're always going to look left to right and up and down. So do these things increase or decrease? And then not only do you need to know if they increase or decrease, but you need to be able to explain the why. Why are they increasing or decreasing? Okay? So for atomic radius is a measurement, the simple way of the size of an atom. Okay, just like the radius of a circle, if you measure from the middle of the circle to the outside edge, that's the radius. That's what atomic radius is. And yes, we actually can measure the radius of atoms. This is an actual measured value. Obviously, teeny, teeny, tiny unit called an angstrom. Yeah, but it's so small. An angstrom, I can't remember the shape of it. Okay, what do we want to do first? Left to right? Let's go up and down. Balance out. Okay, I'm skipping to this one first, okay? So what I'm going to do, everybody, is on this first trend, is I'm going to walk you through and give you the answer of the trend and the why. After this first one, before I give it to you, I'm going to give you a moment to think for yourself. And I encourage you to come up with an answer, even if you're not sure it's right. Because like I've said before, you'll learn a lot more from making a mistake and fixing it than just waiting for me to give it to you. Okay, but I'll kind of do this first one to get us rolling. So the trend is for atomic radius, that atomic radius tends to increase from top to bottom on the periodic table. Okay, so keep in mind when we say top, bottom, left, right, we're referring to the table. Okay, so as I go from hydrogen down to lithium, sodium, potassium, rubidium, cesium, francium, they're getting bigger in size. Okay, this one's a pretty logical trend going down. The reason why they're getting bigger is because every row is a new energy level. So hydrogen, this is just like a rough picture, would be like this. Lithium has 2 rings. Sodium has 3 rings, so on and so forth. Another energy level makes the atom bigger. Pretty significantly, actually. Like there's a pretty big difference in size. It's not like a little bit bigger, it's a lot bigger. So, okay? Now, left to right. As I go from the left to the right of the periodic table, atomic radius decreases. Okay? So as I go from left to right, atoms get smaller in size. Now this one's not as intuitive, good word there, because a lot of you would argue, well, wait, Xenon's like way bigger, like 131. Rubidium's like 85. But that's just its mass, not its actual physical size. So keep in mind, like what we said, everything is going back to one of two things. Distance and Zeph. As I go across the row on a periodic table, am I adding another ring at any point? No, because rings only get added when you jump down a row. But what am I adding to my atom? More Zeph, more protons. So what happens is that as you go across, the force of the nucleus increases, allowing it to pull those valence electrons in a little bit more. Now it's not a drastic difference. If you look at their sizes, it's a very small change. Up and down, very drastic. Left to right, very small. But if you compare the ends, neon to lithium, it's pretty significantly smaller in size because the stronger the Zeph pulls those electrons in tighter. Good discussions. Let's check it and make sure we're on the right track. So we're wanting to put them in order of increasing size. So we need to go from smallest to biggest. Okay? Now, the first thing I look for is we know from the trend, the farther to the left and higher up it is, the smaller it will be. So since they're in a little square on the periodic table, carbon is the farthest to the left and up. Right, sorry. So carbon's going to be the smallest of my list. Okay? I also can go off and say, I know aluminum's going to be the biggest because it's the farthest down and to the left. Okay, a lot of times when I have to order things, I try to find my endpoints first and then deal with the middle. Now, between boron and silicon, it gets a little weird with diagonals because one is further to the left, but one is further down, so you got to weigh which makes a bigger difference. Matt?
So is the largest atom we know of Fr?
Yes. Yeah, very good. And what would be the very smallest? Good. Yep. So between these two, what makes a bigger difference? Going across or going down? Going down. So we're going to have carbon is less than boron, which is less than silicon, which is less than aluminum. If you have that on your paper, you can have a smiley face.
Yes.
No. Okay, does someone want to read something and get a smiley face?
Yes.
Okay, everyone listen here. So as we go through these trends, I've also put in, so like I said, you need to know what the trends are to be able to order things. But if it's not a multiple choice question, or even sometimes with multiple choice questions, you also need to be able to justify your orders. There's ways to justify and get 0 points. We don't want to do that. So this is a do and don't list of a justification. Okay? All right, Corbin, so will you read the do's and don'ts in this first box? You can read off your paper too. What?
Well, you just called me Corbin, but that's okay.
Oh, I'm sorry.
Corbin, isn't that your name?
Yeah, Corbin. Everyone call me Corbin.
Okay, so just the first box right here.
The first box. This is not the same thing. Oh wait, I'll just read off there. Rate of effective nuclear charge, Zeph, increases the effective force of the nucleus, and therefore pulls the electron cloud closer to the nucleus, resulting in a smaller atomic radius.
Perfect. So that is a good justification of why they get bigger. A period, by the way, means a row. So this is saying why they get smaller going across a row. Okay, now read what you shouldn't write as a justification.
Don't simply stating that atomic radii decrease from left to right across a period. You will not earn points.
So one of the biggest things is just stating a trend doesn't justify the trend. That's just memorizing the pattern. You can't just say, oh, well, they get smaller going left to right. Well, why? Why do they get smaller going left to right? And it's because of the Zeph. So when you have to practice and when we are justifying these things, make sure you're answering the why of the trend and not just the trend itself. Okay, so we won't read through all of these in our notes as we go just to save a little bit of time, but it would definitely be a good thing to review as you're working on the homework and things like that. Okay, have a smiley face. Okay, second trend. So first trend was atomic radius. Second trend is ionic radius. I guess I should say more ion radius. What this refers to is when something becomes positively or negatively charged, how does its size change? So the way this picture works, if you can't quite tell, is everything that's gray is representing the atom as a neutral atom. The colored version is showing when it's changed to an ion. The pink ones are all cations, meaning they're positive, and then the blue ones are all anions, meaning they're negative. Okay? So the trend is this. When something loses electrons, its atomic radius decreases. When something loses electrons, its atomic radius decreases. Now, once again, that seems fairly logical at first, like, hey, you lost something, so it's going to get smaller. But saying that losing an electron makes something get smaller is kind of false, because in a sense, electrons are teeny, 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 tiny. So anyone have an idea of why it gets so much smaller? Jordan?
It gets smaller because if you lose electrons, that means it's going to be more positively charged, so there's more protons, so like the force of them pulling in will make it smaller.
That is definitely part of it, yes, because you have less electrons, more protons, so more force pulling in, but there's something else as well, but a good thought. Matt?
Say you only have 2 electrons on the valence shell. If you lose both of those, then that entire shell is just gone. So it's
Yeah, we didn't really just lose the one electron, we lost the entire shell that it was occupying. Right? It'd be like the entire back row is gone. Right? Makes it a lot smaller. Yeah, Sam? So the trend is that when an atom loses electrons, the resulting cation is smaller.
Thank you.
Yep. Yeah, Eli.
So when you're doing like what we did with like the carbon
Uh-huh.
how would you do that with like this?
Like how would you order them with this?
Yeah.
Hold that question for one moment and we'll do a practice problem with it. So then on the negative side, oh yeah, Connor.
So if it gets so much smaller because it loses the shell
Yeah.
when it loses that one electron, why does it get so much bigger when it gains electrons? Because it would just be filling a shell instead of making a new one.
Great question, right? So on this side we're gaining now and we're not making a new shell. Right? When tellurium gains 2 electrons, it's still on the same row. So great question of, yeah, why is it getting so much bigger? Because electrons are tiny, so you can't really just say like, oh, it got more electrons, so it made it bigger. Any thoughts of why they get so much bigger? Any hypothesis out there? Jordan, you have a thought?
Because of the shielding,
Ooh.
because like all the other electrons are like shielding it from it, so it's like the ones that are gained are like pretty far out.
You're on the right track, but there's something with the other electrons. It doesn't cause a shielding because they are added to the outside. So it'd be like me adding a student next to Taylor. So we add a student there. They're not going to shield because they're still on the outside row. But how does that student feel about the rest of the students?
Doesn't like them.
It's the repulsion. Electrons have such a strong repulsion to each other that when you add another one to a ring without adding more protons, because that's the thing, right? I now have more electrons but not more protons, it causes the ring to have to expand.
So if we like put another student over there, like the back row just kind of shift back a little.
They're all going to push each other farther away. Right? I imagine it as like, imagine the back row, we won't make them do this, this would be funny though. So imagine them like playing ring around the rosies with each other,
You can do that.
okay? But like, in playing ring around the rosies as electrons, you're like as far away as you can be from one another, right? You add someone else who also repels, and everyone has to expand to fit them in. So, yeah.
But like, then why doesn't the positive cations, why don't they get way smaller then? Because they're both losing and they're losing a shell.
Well, it kind of depends on what it is, right? Like some of them do, like some of them are pretty drastic in size, right? Like, I mean, this one, that was the original and then that's the change, right? The difference is if you only have something that only has 1 on its outside valence shell already, that one doesn't repel that much farther away because it doesn't have any other repulsion. So its shell size isn't that big. But then you can see that the more you have, because you see how there's like a much drastic difference between when you lose 2 electrons or 3 electrons, is because the more you have, the farther out it's pushing this shell to be itself. Because that's what's interesting is these shells, right, these energy levels aren't a set size. They're dependent upon how many electrons are occupying them. So, does that make sense? Great question. Ask my piece of that. Any other questions on, and then we'll get to Eli's question with doing a practice. Okay, so let's have you try this. Like this, see how we did for smiley face? Okay, so we have calcium 2+, magnesium 2+, and then normal calcium. So once again, sometimes when you're trying to compare things, it's best to just compare 2 of them and figure out their relationship and then worry about the next one. It can sometimes be overwhelming when you have to do 5 of them to figure it all at once. So what I would say is, well, between calcium and magnesium, no matter what, both the calciums are going to be bigger, even the ion form. Okay, so I know that magnesium should be the end of my list because I'm doing decreasing order. Now, between calcium without a charge and calcium with a charge, we said that when something becomes positive, it's getting smaller. So you should have calcium is greater than calcium 2+, which is greater than that. Have a smiley face, everybody.
Yes.
I think you got it right. Questions on that? So that's our second trend, is ionic radius trend. Yeah.
So if it was calcium +2,
Uh-huh.
how far does that move down? So that would be the equal size of the iron.
So you went the wrong direction. So calcium 2+ is like argon.
But it's not like that. It's the same size.
But it would have very similar size, yes. Because now it has the exact same number. It actually probably would be because it has the same number of electrons as argon, but since it has more protons than argon, it probably would be a little bit smaller. But it would be really close. So, okay, questions on, look over your list. These are the do's and don'ts for ionic justification. Once again, you cannot just say that the ion is bigger because it has more electrons. Electrons are really, really small, so that doesn't totally make sense. Why? It's because of the repulsive force between the electrons. That's what causes it to get so much bigger. Okay? All right, third trend. This thing known as ionization energy. Okay? By definition, ionization energy is the minimum energy required to remove an electron from the ground state of an atom. So, you want to write this equation down maybe underneath the definition. I can't write up there, so I'm going to write over here. So this is an example of what ionization is if I take sodium and I put energy into it, I can make an electron come off. So this is, once again, it's so much energy that it doesn't just get excited, but it gets removed. But it's not quite to the extent of a PES where we remove all of them. We're just taking away one. Okay, so this is an equation for ionization energy. Now the value that can be found in a lab, for this one in particular, is 496 kilojoules per mole. Okay? Now what this is right here, and we'll talk a ton about kilojoules and other units and things, for now recognize it's a unit of energy.
Isn't it used in physics?
Yep, you'll use it in physics a lot too. But it's just a unit of energy, okay? Now something you need to understand about energy, if you don't, there's no such thing as negative energy. When we have negative signs or positive signs, it's a directional thing. Okay, so what this means in terms, because it's positive, is to make this equation happen, I have to put in this much energy. if the energy is negative, then the atom itself is actually giving it away. Okay? Now, it's kind of weird, but just play along with me here. So with our analogy, once again, that we're an atom, ionization energy is like the cost it would take for someone to come and take Ethan away. So that's, in a sense, that's what it is. How much do you have to pay the atom to take off an electron? In this sodium's case, we have to pay 496 kilojoules. Okay? So the lower this number is, the more willing an atom is to give away its electrons. The higher it is, it's a lot harder to get those electrons off. Okay? So now let's look at the trend. So let's start with, let's go up and down first. So don't shout it out loud. I want everyone to think for themselves on this one. As I go down a group, a column, does ionization energy increase or decrease? Just think in your head for a second.
Wait, what was the question?
So as I go down a group, so comparing sodium to francium, does ionization energy increase or decrease? Or another way you can think about it, is it harder or easier to pull off an electron? The little bird in the window. You have the answer? Okay, I want everyone to do this. Everyone point up if you think it increases, point down if you think it decreases. And once again, if you're different than everyone else, that's fine. I just am glad that you're thinking it through. So if you think this blank should be increased, point up. If you think this blank should be decreased, point down. Good. So the correct answer is it does decrease. So Matt, do you have an idea of why?
Because as there's more shells, the electrons don't feel as much force from the nucleus because of the blocking principle thing. And so it's easier to just pull them away because they don't.
Perfect. It's all about distance, right? If I was francium, my valence electrons would be like down the hallway. Like someone comes to take them and it's like, oh yeah, go ahead. Like you're so far away, right? Like they don't feel that force because they're so far and there's tons of shielding that's going on. So have a smiley face, Matt. Good job.
Wait, so the protons, they attract the electrons?
Yes.
Okay. Okay.
Okay, let's figure out left to right. So don't say it out loud, but what would we put to fill in this blank? So as I go left to right, does it increase or does it decrease? So think to yourself for a second. And then once you have a choice, point up for increase, point down for decrease. Good work. So it does increase. Anyone feel like they can justify why? Yeah, go ahead, Jordan.
Because there's more protons, so the binding energy increases.
Yeah, much stronger Zeph, right? They're not any farther away as you go across, but the force of the nucleus is stronger, so it's a lot harder to pull them away. Very good. Have some my face, Jordan. Okay, all right, let's go ahead with your table buddy now and sort these 5 in order of increasing ionization energy. Ready, go. Ready? Check your answer with mine. Make sure we're all on the same track. Okay, so you should have potassium. Let's see, we're doing increase, so I gotta do is less than sodium, which would be less than phosphorus, which would be less than argon.
I said I was thinking what they were doing, so.
Any questions? We didn't get it right and we don't know why. Okay, now sometimes people wonder, like certain things would be pretty hard to compare if you get some weird diagonal things, like it's like it's further to the left, but this one's farther up, like stuff like that can sometimes be kind of tricky. And honestly, like I've never seen them do things like that without giving you data, because that's what they expect. Is they just expect you to be able to compare to get idea about things. Now, so far, we've actually only been talking about what's known as the first ionization energy. The reason why it's the first is because we're talking about just removing one electron. But it is possible to have a second ionization energy, or a third, or a fourth, or a fifth, and the trend is now different and can vary. So the trend that we just talked about, where francium would have the lowest ionization energy on the whole table, and helium had the highest ionization energy on the table, only applies to the first ionization energy. If we're talking about second or third, we have to take something else into account. Where's that? Okay, so we're going to take a look at this little diagram here.
So it's S1S1.
So this shows you the ionization energy. So this is the first ionization energy. Second, third, fourth, fifth, sixth. Okay? So, oh yeah, go ahead, Matt.
So it's technically possible to just create a nucleus with no electrons.
If you put enough energy in.
And has that been done?
So that's what the PES does.
Oh.
Is it shreds the photoelectron spectroscopy.
Oh yeah.
Yeah. But no, still a good connection. That's how these are connected. Is this is only supplying enough to take off a few. That one supplies so much they just come off. Okay? Alright, so pretend with me here, ready? How many do we have? 7? Okay, so we're gonna be chlorine. Oh wait, chlorine got cut off. Let's pretend. Okay, ignore those 4, no offense, pretend they're not there. And let's say we have 3 valence electrons. Okay? Okay, so if we had 3 valence electrons, we could be like aluminum. Okay? So here's how it could this is once again kind of just trying to make a connection here. The idea of how it could work. So to come and take away Ethan, if we're aluminum, would cost 578 kilojoules of energy, first ionization energy. Okay? Then, to come away and take away Tylen, it's going to cost 1,817. Okay? Now, to take away Taylor, it's going to cost 2,745. But now, watch this, everyone. If someone tries to come take Olive, it's going to cost 11,577.
Oh. Whoa.
So, does anyone recognize what's the significance of this big jump?
It changes the shell. Because it changes another shell.
Atoms do not want to give up their core electrons. And in nature, they don't. That's why the valence are the only things that move in nature. In the lab, we can put energy in and make them come off. But in bonding, things don't ever give up more than their outside shell because of that strong binding energy it has. Yes. So you can predict actually an atom based on this data. If you see ionization energy and you see a very big jump, that tells you at least what column it's in because of where it loses its last valence electron. Yeah, Eli.
So how would you determine what the first ionization would be? So sodium, how does have 195? How would you find it on this?
Like the actual value?
Yeah.
Why is sulfur down?
And then what is
Isn't it
nitrogen?
to do with how many?
So they actually you can go into the lab and using equipment, they calculated these values. So for you guys, that's why there's no way, you would never have to say the values. We're more on the comparison line of things, but good question. Yeah, Calvin?
So with the chart, the first ionization, I feel like from top to bottom, it's going, the numbers are going up for how much you need.
Yes.
And then on the rest of them, it's all going down with the event. Or it's kind of, I don't know, it's not. I was kind of doing that with the 4,000, I don't know. I was just thinking out wrong.
No, it's just because of this jump, right?
Yeah, it's a jump.
That makes the trend not clears because it all depends on once you start hitting the core. So, yeah, Connor.
So why does phosphorus have a higher first ionization energy than sulfur?
So that's a good observation because that isn't totally true. Wait, where am I looking? Right here?
With that.
To our trend. Does everyone see that? Our normal trend is that generally it should get bigger as we go across. Now with any trend or with anything we learn in chemistry, you should learn that the favorite word of chemists is exceptions. Right, there's exceptions to the trend. You're never expected to memorize the exceptions, But seeing them, you should be able to provide a possible reason. To justify trend exceptions, go to their orbital diagrams. So if I have the orbital diagram here, and only when you draw orbital diagrams for trends, just focus at the end. You don't need all the stuff that's filled, right? So for phosphorus,
It's full.
not full, but what do we call it?
Half full.
Half full, which is a form of stability, versus if sulfur, what happens with sulfur if it gets one away?
It's half
Half
full.
full.
It becomes half full. So it costs less to remove this because the end result is a little bit more stable. That's the idea of energy cost. The more stable something becomes, the less you have to pay to make it happen. If it makes it unstable, you have to pay a whole lot, which is why with argon, even the first ionization energy is,
Pretty
wait, this is removing, not adding. So it'd be like, well, anyways, you got what I was trying to say, right?
Yeah.
Did that answer your question, Connor? Good observation. So whenever, if there's ever a question where you have to explain a discrepancy in a trend, think of the boxes and arrows, and normally it deals with the half-filled or full-filled idea. So, yeah, Calvin.
You look at the ones with aluminum, silicon, phosphorus, and kind of that area,
Uh-huh.
all the way across, besides the staircase, but it flips where it goes, if you look at the second ionization, it goes 1800, then 1500, and 1900,
Uh-huh.
and then it goes the third ionization, it goes 2700, 3200, and 2900. So is that because of the half pipe, or why does it go up or down, or down and up? Yeah, up and down. You see what I'm talking about, though?
Yeah, because it's not like a complete equal change from one to another, right? That's what you're saying, like the change from one to another is not the same every time.
Yeah.
Yeah, I would guess, because like with silicon, because with silicon, so this is a second. So if I remove 2 from silicon, we've actually emptied the P shell now.
Okay.
So the 3 things that help it be stable are empty, actually, half-filled, and fully filled.
Oh, okay.
So, yeah, good observation though. Any other questions about ionization energies? Okay, let's have you try this problem, maybe, with your table buddy.
NaCAS.
Okay, so between those 3, pick which one would have, without looking at the chart, keep in mind, you're not going to have these charts, so don't look at the chart, but between those 3, which one would have the highest second ionization energy? Okay, so for the homework, if you didn't pick it up, some of this you can do, so I would say get started on 1.9, but if it talks about electronegativity or electron affinity, skip it for now. Okay, we can though, we should still be able to do all the reading, so make sure you take a picture, write it down.